Welcome back, everybody. So we're in part 2 here of the infinite geometric series and induction notes. We're going to look at these few remaining examples of infinite geometric series here below, and then we'll move on to induction. So up at the top, just a reminder of the notes that we worked on last time. So deriving that formula for the infinite geometric series, discussing divergence and convergence of geometric series, and how to determine between those. So for these examples, the first one at the top is similar to the two final examples from the previous notes. And then these three are really more a specific application of figuring out how to take a repeated decimal and rewrite it as a fraction using infinite geometric series. So for that first example up at the top, we'll look at our series, which is 1 plus 1 over rad 2 plus 1/2 plus 1 over 2 rad 2. So if we look at each of these terms, if we took any of the ratios between them, we would see that obviously we're multiplying by 1 over rad 2 or rad 2 over 2, if you wanted to write it that way. So R is equal to 1 over rad 2. So if we want to find the sum of the series, we need to first figure out if it converges or diverges. So 1 over rad 2 that's equal to approximately 1 over 1.414 ... So clearly that's less than 1. So we definitely have convergence. So now the series definitely converges, and now we can use that summation formula. So we'll get that S is equal to the first term over 1 minus our common ratio. Now, if you use so our sum is 1 over 1 minus 1 over rad 2, and that's going to equal 1 over rad 2 minus 1 over rad 2, which equals rad 2 over rad 2 minus 1. So if we wanted to leave it in that form, we could, and that's a perfectly fine form for our answer to be written as. But if you want to rationalize, you can rationalize. So we would end up with 2 plus rad 2 over, on the bottom we would get 2 minus 1, which is equal to 2 plus rad 2. And that would be the sum of our series. These repeated fractions, and some of you may have seen this before. So we'll just note that what we can do is write each repeated portion as a separate value. So 0.43 would be 43 over 100. And then the next term would be 0.0043, which would be 43 over 10,000. And then the third, 0.000043, 43 over million, etc. And we can say that that's an equivalence with that fractional expression. And so then we can note that between each of these terms, we're multiplying by 1 over 100. All right, so that is going to equal our common ratio. So if R is 1 over 100, that's clearly less than 1. We know that A sub 1 is 43 over 100. So then our sum is going to converge to 43 over 100 over 1 minus 1 over 100. So this is actually going to work out pretty nicely. So we'll get 43 over 100 is equal to, if I find a common denominator in the denominator expression, we'll have 99 over 100, which simplifies to 43 over 99. And you could put that in your calculator to verify. So just a quick use of geometric series to convert decimals to fractions. So the remaining two examples I'll let you do on your own. I'll note the answer for the second one. Will give you 123 over 999. I'll leave that for you to verify. And then the third one is slightly different because now I'm skipping that 12 over 100 term and just starting with 12 over 10,000. So see if you notice a pattern and see if you can figure out what that third example will be. And you can check the notes online to verify your answers for both of those. And so moving on then to the second part, and this is going to be really the main new idea for these notes, which is going to be mathematical induction. Some of you may have seen this before. So we're going to discuss how it works, work through an example together, and then the next part of the notes will work on some specific examples. So mathematical induction is a proof method for proving that a statement is equivalent to another statement. It's a very powerful method of proof, but it's also kind of a very tricky and abstract proof method. So it's going to be something new for many of you. So we're going to look at kind of how we set it up, how we use it to confirm our conclusion, and then we'll work through some examples. So our first example then is the following claim. So the sum of the first n natural numbers is 1 plus 2 plus 3 plus 4 plus all the way up to some value n equals n times n plus 1 over 2. Is this true? Let's test some cases. So we know ahead of time, because we've actually already proved this, that this is really just the arithmetic series, right? Where this n plus 1 over 2 is really n times a1 plus a sub n over 2. So we know that this is actually going to be true, but we're going to actually prove it by induction and show a second way of proving that arithmetic series. So it says let's test some cases. So if this is true, it better be true for, n equals 1, n equals 2, n equals 3. So if n is equal to 1, I'm going to compare both sides of that equation. So on the left, obviously, I just have 1. And on the right, I'm going to have 1 times 1 plus 1 divided by 2, which is going to be 2 over 2, which is 1. So it's definitely true for n equals 1. Let's try it for n equals 2. So that would be 1 plus 2 is equal to 2 times 2 plus 1 over 2. So let's see if that's also true. So we get 3 on the left. On the right, we get 2 times 3, which is 6, divided by 2 is 3. Okay. So we can see for these first two cases, clearly these two statements, these two expressions are going to be true for each other. So the question then is just below. Is this enough evidence to prove that it's always true? Right? So if I show you these two cases, is it always true? No, it's not going to be true necessarily. So we can have it work for a certain number of cases and then it's going to fall apart. So we need to show that it works for all cases. So the question is, how do you show that it works for all cases? Right? Can we write out an infinite number of examples? Obviously not, right? We can't show that we can't do n equals 3, 4, 5, 6, 7, 8, out to infinity, because infinity never ends, right? We have a larger and larger value that we can continually check it against. So here is how induction is going to work. We're going to assume that the mathematical statement is true. for n less than or equal to some number. We're going to call that k. It's traditionally how we write it out. So we're going to assume that the statement is true for n less than or equal to k. And note k is just going to be k. It's not going to be a specific value, but we know that k in this case could be 2 or it could be 1. So for at least those two values, k would exist as a possible answer. So if we assume that the statement is true for n less than or equal to k, then we're going to show that it is true for n equals k plus 1. And that's really the key. So we assume that it's true up to some value k, and then we show that it's true for n equals k plus 1. And the power of the proof is that k is not an actual numerical value that we're considering, but it's any up to any value, which means that if it's true for k and it's true for k plus 1, then I can repeat the process. So once I find k plus 1, then I can let that be k and do the same process again, and again, and again, and again, and repeat it ad infinitum. So let's actually write the proof for this statement. Okay, so the way that we're going to break it up is into 3 pieces. So we're going to have what we started with, which is called the base case. And so base cases show that it's true for at least one value. We only need it to be true for one, but you can do more if you want to. So n equals 1. So that we've kind of already shown. So 1 is equal to 1 times 1 plus 1 divided by 2 equals 1. So that's true. And then once we have the base case, then we're going to, let's actually zoom a little bit here. We're going to make what we call the, induction step. And this is the key for our proof. So the induction step is going to be our assumption. So we assume the statement is true for n less than or equal to k. Now, what does that mean? What that means is we're going to assume that 1 plus 2 plus 3, so i.e. that is so now sum of those numbers up to some value k is equal to k times k plus 1 over 2. Zoom back out. So we are going to assume that this is true. And we know that this is true at least for k equals 1, because we showed it above in the base case. So it could just be 1 equals, 1 plus 1 over 2. We could show it for more cases if we needed to. So if you need to do that to kind of convince yourself, feel free to. And this is the key step, because once I've made this assumption, I can now use this statement in my proof. Okay, so this is kind of the key here. So the last step then is the actual proof portion. And before we get to that proof portion, though, I want to quickly look at if n equals k plus 1 for my statement, so that's 1 plus 2 plus 3 plus n equals n times n plus 1 over 2. If n equals k plus 1, and I substitute it in, what would it look like? All right, so the first n becomes k plus 1. The second part becomes k plus 1 plus 1. So I should get k plus 1 times k plus 2 over 2. So if this statement is true, this should be what I end up with for that k plus 1th case. Okay, so every time you do an induction proof, you want to kind of do this step ahead of time to get the expression that we're looking for. This is what we are looking for. All right, so let's go back to our notes then. So for our proof, our first step in the proof is just to rewrite our assumption with that next term written. So I'm going to have 1 plus 2 plus 3 plus ... plus k is equal to k times k plus 1 over 2. Okay, so far this statement is true by our assumption. And then what we're going to do is we're going to add on the next term. So the next term on the left would be k plus 1. And to balance my statement, I'm going to add it to both sides. That's going to be our key. And now we can ignore the left-hand side because that's just going to stay fixed. So that is going to be our starting statement. We're going to move to the right and look at this statement here and do a little bit of algebra. So this is going to equal k times k plus 1 over 2. And then the second term, I'm just going to find a common denominator. And then now that I have a common denominator, I can look at both terms, and I can see that both terms have a k plus 1 in common. So I'm going to factor out k plus 1. What am I left with? K plus 2 all over 2, which is what I was looking for in the first place. Okay, so that n equals k plus 1 step beforehand, which is not officially part of your proof, it's kind of like your side work. That's telling you what you're looking for. And what we just showed is that by adding the next term in our series, we get that exact expression, and our proof is done. So thus we've proved by induction that 1 plus 2 plus 3 plus 4 plus ... n is equal to n times n plus 1 over 2. And note, those same 3 steps are going to be part of every proof. Base case, induction step, and then the final proof statement where you're working out the algebra. All right, so that's going to be it for now. We'll look at the remaining examples in the final part of the notes next time. So until then, take care.